The photoelectric effect. Here's the next experiment and explanation, which again hinted at and showed the need for quantum mechanics, where classical mechanics was failing down here at that microscopic world. And if the black body radiation was the idea that you heat something up and it releases photons of light, the photoelectric effect is essentially the opposite. If you shine a light onto something, it could actually release the energy, maybe as heat, but maybe as actually electric current. That is to say, you shine a light on something, where does that energy go? It could be released as electrons flowing out. This is called the photoelectric effect, and it's what we use all the time in like solar power. If you take a solar panel and sunlight shines on it, it can create electricity, right? It creates an electric current, and exactly what we're talking about. So, light shining onto a metal, an electron is ejected and creates this idea of an electric current. Classical mechanics here, if you looked at the laws classically, predicted that as I shine brighter and brighter light on it, so as the intensity increases, the strength of the current should get stronger. So we should get more amps out of this. Unfortunately, this is not what's observed. Again, a failure of the classical mechanics when applied to the microscopic world down here. And here is a figure from the text illustrating what does occur. If we shine here 700 nanometer light, they got it as red because that's down in the red region, and we shine it onto this metal. I don't know exactly which metal they're using. They use different ones, can all work. No electrons were ejected at all. No matter how intense we made the light, nothing gets ejected. No current. Doesn't work. It just sits there. If you drop that wavelength to 550, keep in mind, a lower wavelength means a higher frequency and therefore a higher energy. So if we use green light, which is a higher energy light, and we shine it on it, hey, we get an electron being ejected. And we can detect it. We can see that current, hook up a meter, and we can measure the current. The electron comes off with a maximum velocity of 2.96 times 10 to the 5th meters per second. So measuring how fast that electron comes off. Increase the intensity of this light, and you do increase the voltage, or not the voltage, I'm sorry, the current, the amperage. All right, but they all have the same kinetic energy. Let's go to even a lower wavelength light, some purple light, some violet. Again, that means an even higher energy. What happens? Hey, we still get an electron coming off, just like we did with the green. We still get the same current. The amount of electricity coming off is the same. But interestingly, the ejected electrons are moving faster. They have a velocity now of 6.22 times 10 to the 5th meters per second, instead of back here, it was only 2.9. All right, so they've more than doubled their kinetic energy. All right, so we're seeing here that a low energy light, the metal doesn't even care. It doesn't absorb it. I guess it just bounces off and it goes somewhere else. If you get the green light, now all of a sudden the metal seems to care about it. It absorbs that energy and it releases it as an electron with a certain kinetic energy. You go to even higher, hey, it still absorbs it. It still releases that energy, the electron, I'm sorry, but it releases it with more kinetic energy. It's like it's converting that extra energy to a faster electron, so more kinetic energy. So this is what's actually observed, which is totally different than the classical prediction. So how can we explain this observation? Well, Dr. Albert Einstein actually was the one who proposed an argument that would explain it. And what do you know? He invoked the idea of quantization to do this as well. Okay? If you graph out, and here's how it works. If you graph out the velocity of the electron compared to the frequency of the light, again, as you have low frequencies, you do not get any electron released. But then as you hit this, what he called the threshold frequency, now you're getting electrons coming off, but they're going slow. If you go to higher energy, that is to say higher frequency light, now they go faster, and as that goes up, you go faster and faster. Yes, so you notice there's some minimum, some threshold frequency under which you just didn't get anything. And that was critical. That was the idea that if you quantize the energy, All right? And if you need this threshold amount, if you will, to carry that electron away, then the incoming has to be at least that much. And if you get a packet of photon fuel which has less than this quantized amount that this metal can absorb and therefore release an electron, it's not going to interact and it's just going to bounce off. Right? You've got to have at least that small size of quantized energy. Right? And then once you do break it off, this is like kind of what I talked about before, you need this initial amount to break it free, and then the extra amount is going to be taken up as, oops, sorry, thought I bumped my microphone there, is going to be taken up as the kinetic energy of it. Okay, all right. This particle light, again, is called a photon. And under Einstein's explanation of a quantized amount of energy that these photons can carry, and therefore also a quantized amount that the electrons, or I'm sorry, the metal can absorb and then release an electron. If you increase the intensity, the increase in the number of electrons occurs, but not their kinetic energy. Talked about that before in the graph. If you increase the frequency, you increase the kinetic energy of it. However, if you're below the threshold, you don't get anything at all. Again, explainable if you quantize the amount of energy that we're talking about. So that's the photoelectric effect. And taken together, these two key experiments illustrated that light, as we're shining it or releasing it, light has a particle nature. Now, we already knew it had a wave nature, and that wave nature didn't go away. We still talk about frequency and wavelength and amplitude, right? And we could do more as well, such as a slit or a double slit experiment to illustrate the properties, the wave properties of light. That all works just fine. We're not going to go into it here, but it definitely has wave properties. But these experiments show that it also has particle-like properties. At least when you talk about the energy of them, the energy is quantized by them. And light doesn't just come as this continuous wave, it comes as packets, if you will, of energy, photons of energy, photons of light. All right, so we have a wave-particle duality that we're observing. Line spectrum. Here's another illustration of, and this is probably even more important for chemists now, line spectra, another illustration of the quantized nature of light and energy in particular. Light. Here's the idea. This black body radiation, right, if you emits it, you heats a matter up, it emits light. What if you take a very pure element, not a mixture, not a compound, but a pure element, right, and you heat it up and you take a look at what kind of light it emits, right? So pure hydrogen gas, for example, pure helium gas, right? The gases are easy to do actually, because you can put them in a little tube, shoot some electricity through that, and boom, they'll emit a light, like a little light bulb. Okay, and so you can very directly take a look at what that light looks like coming off. This way of investigating the emitted photons that are coming off of a pure element is what we call a line spectra. What does it actually look like? Is it all the different colors, right? Or is it just a few mixed together, right? The line spectra. And it's called line spectra because what we found actually is that different elements emit just a little line of light. That is to say, maybe nothing, nothing, nothing if I'm looking at different wavelengths, nothing, nothing, and then bam, I hit, I don't know, 610, and bam, it emits right there at 610, and then it goes back to nothing, 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 and bam, it emits now at 580, or well, I'm making those numbers up, but that's the idea. Only very particular lines, very particular wavelengths do these pure elements actually emit. Right? So if you look at light emitted by hydrogen, or pure helium, or pure krypton, or whatever, they're going to have a different color because, again, they're emitting very different but very precise, thin regions, bands, if you will, of wavelengths. All right. Now, classical mechanics doesn't predict that. Classical mechanics predicts that you should get the full spectrum emitted. Full spectrum, because you're going to be having some of them at a low temperature, some of them at a higher temperature, you know, when you shoot the electricity through, and we should be able to just see this full, every color of the rainbow, and we should be able to get all the way from reds, yellows, greens, the whole thing, full spectrum. That's just not what's seen. And we're going to do this in lab if so you can see this yourself. Here are different pure elements. You shoot some electricity through them to heat them up. Here's where they actually emit the light. And so sodium, it emits a line of kind of reddish orange light, and several here in the yellow range and a couple in the blue range. All this black regions out here, it just doesn't emit it. It doesn't happen. And so the light you'd see coming off of a sodium is, well, you'd have a little bit of red, a little bit of blue, a lot of yellow mixed in. And so it kind of has this yellowish tint. And again, sodium streetlights, they have a certain particular look to them, and they are kind of a yellowish sort of a light. Pure hydrogen, we see 4 lines. We see a red line and a blue line, and down here in the purplish, 4 of them that were emitted. Calcium, quite a bit more lines, but still individual line spectrums is what we can pick out. And by the way, how do we do this? If you look at it coming out, you excite it, the hydrogen or whatever it is emits these photons. If you take that light and just put it through a prism, you know how a prism takes sunlight and it spreads it out into the full spectrum, you can see the full rainbow. Same idea, except instead of putting sunlight through, you put the light coming off of the hydrogen through. And it's going to spread it out, but when you spread it out again, you find out, hey, it's not the full spectrum, it's just little lines from it. Here's mercury and its various lines. So those are line spectrum, and this is what we observe. And again, classical mechanics does not predict that at all. All right, Johann Balmer was looking at and thinking about these line spectrums, right? And he's looking at hydrogen gas, which has these 4 lines coming off of here. And again, as we saw before with blackbody, he couldn't explain why, but he did figure out a nice way to predict what these lines are. And by predict, I mean exactly what wavelength they come out as. He saw a pattern, in other words, and he found the mathematical relationship in that pattern. Right? And here it is. He found this equation predicted the right wavelength. Now, he's got it as a reciprocal, so if you plug the numbers in here and then you flipped it, you took the reciprocal, you would get the wavelength of the light that his equation predicts. And again, he was only working with hydrogen, right? He got all these other ones, and I don't know, he found that hydrogen, he could predict it. And there's a reason for that. Hydrogen is the simplest atom. It's got 1 proton and 1 electron, and so there wasn't a lot of interactions like between the various electrons to worry about. Again, weren't really aware of this at the time, didn't know why this worked, but now we do. Looking back, hindsight is always 20/20, right? All right, so here's the equation that he predicted, or he used to predict the wavelengths of the hydrogen spectrum. Some constant, some proportionality constant, times, and this is kind of interesting, he said 1 over 4, which is 2 squared, minus 1 over n squared, where n is quantized. And it starts with 3, 4, 5, 6. It starts at 3. Again, not sure just why it would have started at 3, but he found it worked. If he used those numbers, it predicted the right wavelengths of those light. But notice here, this is a 2. It's kind of like maybe there's a 1. 1 squared would just be 1 here, but 2 squared, and then we start at 3. Put a 3 squared, 4 squared. So there's something to this, although again, maybe he didn't understand exactly what yet. K was, again, some proportionality constant that was applied to get the correct scaling on the wavelength to come out in nanometers. Right? And so if you plug a 3 in for n, it would predict the first line here of hydrogen. Actually, it would predict the red line. You put a 4 in, it predicts the blue line, a 5 in, and a 6 in, etc., etc. Rydberg extended Balmer's theory, equation, right? He generalized that equation because he realized that, hey, why do you have to start at 3 and have a 2 squared? Why does it have to, be 3, 4, 5? He realized that actually you could use any of the integers from 1, 2, 3 all the way up if you included not just the visible, but out into the IR and out into the UV. See, it turns out that we can't see those, but we can build machines, of course, to detect those. And when you detect them, hey, it's quantized out there too. And there's more lines out there. It's just we weren't seeing them. Right? And so, again, up in the hydrogen, this is what our eyes can see, but there's plenty more going towards the left and plenty more going towards the right of more quantized lines. So he extended this idea. Kind of looks just like it, right? 1 over lambda equals some proportionality constant. And instead of just 1 over 2 squared, he said, hey, let's let this be N1, or the initial, N2 being the final, right? And so and N2 being the larger number, so if I started with a 2 over here, this one has to be at least a 3 and a 4 and a 5, and that's what Balmer had seen. But if I started with a 1, then I could use a 2 or 3 on my second spot. And when you use this and you plug in, you can find what that proportionality constant is. Now, we call it the Rydberg constant, RH, and it turns out to be equal to 1.097 times 10 to the 7th per meter. Per meter, why per meter? Don't forget we're working with these reciprocals, and so you'd have to flip it to actually get the true meters, the true wavelength lambda. But anyway, that's RH, 1.097 times 10 to the 7th per meter, where n's, both n1 and n2, have to be the integers, 1, 2, 3, 4, etc., etc. Not 0, but 1, 2, 3, 4, up and up and up from there. All right, so he did this general kind of boom expansion on it.